Also, like, very easy. Like, even out.
Okay, so today what I'm going to do is kind of like summarize like the thing that I was trying to say last time about the singular value decomposition. What is like kind of what is like the thing that actually remember from it? The proof itself it doesn't matter too much. Just like the projector stopped working, so I couldn't show you the fun application which now I can show you about today. So I'll tell you kind of like what do you need to remember from SVD and like how it's used in practice. So just to kind of like connect it a little bit more um, with other aspects of the course. And you'll see why it's like a very useful result when we get a chance to kind of like apply like the idea is like we will apply kind of like SVD, like a singular value decomposition consensus, but you have to do it kind of like in a clever way. But that's not something that we will discuss today. Okay, so here is kind of like a summary of like the situation. What should I need? Let me see if I can do this a bit stuff. Okay, so in idea in singular value decomposition is a follow. You start with a matrix which is not square in principle. It could be square, but it doesn't have to be. That's kind of like the advantage. So A is a M by N matrix. Okay. Now, just to remind you, the way this is set up, if the matrix is M by N, that means that the matrix, if you think about it as a linear transformation or like as a map, as a function, you know, the input is Rn and the output is Rn, right? And that's like, and this is what the matrix does. Okay. Now, the idea is that you start with a matrix which is not necessarily square, and there are two kind of like obvious candidates for creating like a square matrix out of A. The two possibilities are like the two kind of like square options are A transpose A and A transpose. Because again, if you think about this, let's just check it one more time that the numbers match. So A is M by N, right? So when you transpose it, you get N by M, right? So overall, this would be like an N by N matrix, right? And kind of like the same what happens with the other one, right? This would be N by M, and this one is M by N, right? So in this case, this one gives you M by N. Okay, so those are kind of like the two square options, you know, that you could produce if you start with the matrix A. Kind of like, again, you can ignore the proof. The most important thing to kind of like remember of what I was saying last time is that these, well, are symmetric. Each of them are symmetric. So each is symmetric. Which is kind of like easy to check, you know, just from their definition. So that was the first important thing to know. Another super important thing, it is kind of like the miraculous part, and where like we kind of went on over the proof last time. They have the same rank, and their rank equals the rank of 8. That's kind of where the magic happens here. So, and this is like super important. So that's like your really good part, that the ranks all agree. And kind of like it's related to this stuff about the rank. You know, the matrix A is not necessarily square, right? So if A is not necessarily square, it doesn't even have like eigenvalues, right? We only have eigenvalues for square matrices. But each of these are square matrices. And so the other cool part is that the eigenvalues coincide, like the eigenvalues for these two matrices are the same. So, which again, like it's amazing, like if you think about it just from the fact that they have even different sizes, right? Like what could be like 4 times 4 and the other could be 10 times 10. Like, they have different sizes. So it's kind of like very cool that the eigenvalues are the same. Um, and the last thing that kind of like, I was, yeah, sorry.
Do we also show the eigenvalue sheet?
Oh, that's the thing, like A itself may not be squared, so you cannot compare that to, like, you may not be even able to talk about the eigenvalues of A, right? What I did say, like maybe that's why you're thinking about it, is that I did say that if A happened to be symmetric itself, right? Then the eigenvalues of these one are the squares of kind of like the eigenvalues of A, which kind of makes sense. But yeah, but only if A has, but that's like a very special case, right? But in general, and I'm about to show you some applications. But in general, the matrices that you should expect for A are rectangular. So talking about the eigenvalues, this is kind of like if you actually had to ask someone, what is the eigenvalue of a of a rectangular matrix, the answer should almost be, oh, they are the eigenvalues of these matrices instead. Well, after taking square root, because that way, like, yeah. But up to a square root, that's not like the right answer for what is the eigenvalue of a rectangular. You see? So, right, because the other thing that, is the other cool thing is that all these eigenvalues are non-negative, right? And that's where like the singular values are defined as like they're just like the square roots of the eigenvalues. So the singular values. I mean, you only care about the non-zero ones because they're either zero or positive. Like only the non-zero ones are interesting. But it's kind of like the eigenvalues of this the square root of the eigenvalues of this matrix. And again, the really cool ones, like the ones that are non-zero, go from one up to the rec, right? So are from k equals 1 to k equals the rank. Because the other thing I had said is that you when you write them down, you kind of write them down in a. Oh well, actually, you order them. Yeah, like you order them from in a decreasing fashion, right? Yeah, so this is fine. So the idea is that the number of non-zero eigenvalues in the rank of the matrix, which matrix does the cool thing? Is either the matrix, like they are the same rank, so it doesn't, we don't have to think about it. And then, so the first, you order them because they're all positive, or like, you can order them in decreasing order, and then like, the first one, like, you always start with the largest, singular value, and then you go down. And eventually, as the rank of the matrix, they all like collapse to zero. So like in fact, I'll show you like how this looks like in a moment. And then kind of like the last part. So again, like the cool thing about SVD is that there are so many cool, like very useful properties. And the last part, which is how it's related to the tensor graph that we can say, is that this allows you to kind of like rewrite the matrix as a tensor product. And then this was kind of like the tedious part, so I'm not going to go over it again. But the idea is that you can express the matrix as a tensor product from 1 to the rank of A of like the singular values times UK tensor VK where the decays were like eigenvectors, like, you know. Let me see just to make sure like I'm writing them in the right order and everything. I think it's fine, but I just want to verify that. Yeah. So here, like the decays are like the eigenvectors of A transpose A. Like again, like you normalize them, you orthonormal basis and everything. So like you use like Gram-Schmidt or whatever, like orthonormal, oh, normal. And the UKs are like, you know, the eigenvectors. But in practice, the way people write that down is like what I had. I mean, we wanted to go over this so that we would have like the connection to the tensor rank. But in practice, like the way people write this down is in this way, where like you just use like eigenvectors to make use eigenvectors or column vectors, and you construct the matrices out of this.
Oh, that's sorry. I want to say that like sigma one up to sigma n is greater than zero, because if it's not zero, then we go down by one.
Sigma one up to. Oh, right. Oh, yeah, I see what you're saying. Yes, this one, like this one is strictly greater, you mean? Yes. Right, yes. In fact, I mean, the only exception, like, the only matrix with right is zero, I guess, we go zero, right? Yeah. Right, like, so we don't care about decomposing the zero matrix, yeah, so you're right, like, at least enter the matrix to have, rank one, right? Otherwise, like, this guy to see. But yeah, I thought like like the cool thing with SVD is that they are actually many useful applications. I was just going to show you a couple of applications before continuing because it's not nice to appreciate it. It is like next to the spectral theorem being that you can diagonalize symmetric matrices. It is kind of like at that level of like importance, you know, like it's really important result. Yes.
Well, I didn't come to class.
Mhm.
And like, the lectures were not available.
Yeah, because like the projector wasn't working, so I had to. Yeah.
So like. Well, I guess, sorry, it was, I mean, that's not.
No, but I can actually show you I have my lecture notes in my CAD
Oh.
notebook.
I see.
So if you want to take pictures of them, I can share them. Yeah.
Sure. But like, for now, so what exactly are singular values?
Yeah, they're just
What are they physically?
well, I mean, I don't know, like if you want to like give them like a physical interpretation per se, but what you should think about it, well, I think that would become a little bit more clear, like in the applications that I was going to show you. But they are kind of like you know, what does like okay, like the idea, right, is that these two matrices, like U and B, are supposed to be orthogonal matrices. Orthogonal just means that they are kind of like rotations. It's like they could also do like a reflection, but essentially they're like rotations. So think about them as rotations. A rotation, if I have vectors with me. That's fine. So here's a rotation. Like it doesn't change the length of a vector, right?
Right.
So a rotation. So that means if you think about the matrix that's being formed out of three pieces, the two of the three pieces don't change the lengths of the vectors. So all the change in vector size comes from the singular values. So the singular values are kind of like related to some like the stretching factors like the matrix. It's kind of like a rescaling. It is like the part that's responsible for rescaling the vectors. Yeah. So I mean, I guess that's kind of like a physical interpretation. If you kind of like that's like the part that stretches the space. The other two parts either rotate the space or kind of like put like a mirror because like a reflection is kind of like some sort of like a mirror operation. So it's kind of like rotation or mirror, like you know. And so all the changes in length of the vectors are due to the singular values. That's one word.
Shouldn't there be like, a singular value vector? Which is how.
Well, the way they are,
You, some.
well, like like this matrix is mostly full of zeros. Like if you remember, like I mean, I don't know if you how clear the video was. Like it's this. I mean, let's not let's take advantage of the fact that we have computers, right? So let me see if I can show. I was going to show my computer anyways, like my screen at this moment anyway, so I might as well do it now. Um, I was like, I have. Why does this look so big? I don't really understand what's going on here. Okay, this looks a lot better now, right? Okay, but what I wanted to go over. Oh my God, yeah, I don't know why it kind of like shows this way so weird. Okay. I think there was a cute example on Wikipedia about like so that you could see how it's written down. Where is it? Oh, they don't have like an example here, but like where is like uh just to kind of like show you how it looks like. Ooh, okay. Where is the here? Okay, that's kind of like my point is like I wanted to show you how the matrix sigma kind of like looks like in general. Like yeah, you can kind of like store this as a vector, but it's kind of like
Sigma is a matrix.
it is a matrix, right?
I
Right.
thought that was Tom.
Oh God. Okay, now I understand like the confusion. Yeah, sorry about that. Yeah. Good. I'm glad that we went over the example, right? Like, no. Sigma is a matrix, but it is overwhelmingly a matrix of zeros, right? So the only non-zero entries are like the positive, like the singular eigenvalues. I was going to say eigenvalues, the singular values, which happen to be positive, right? Yes, that's fine. I don't care about methods. Okay. And then oh, cute. This is kind of like the usual friend of rotation by 45 degrees matrix, if you recognize it. And okay, this one is a bit more complicated type of rotation, but yes.
So is the reason that like it's kind of like unless matrix because sigma matrix is not going to be full yet. It'll be like some zeros. So when you expand out in the multiplication, those zeros take over some of the rows.
Well, the compression is still not yet here. I still haven't compressed anything because this is just kind of like a factorization, right? Like
Yeah.
it just happens to be that it is a factorization where there are tons of zeros, right? But that doesn't necessarily tell you that there's compression going on.
Well, we're multiplying right by sigma zero.
Well, but you have to be careful because of how first, like, it's it's not diagonal in the strict sense of the word because it's not a square matrix in general, right? And if you do remember how like multiplication works, like you are multiplying kind of like the columns times like the rows, and that just once you have non-zero entries, that that will kind of like scramble everything. So you cannot just kind of like I agree as a rule of like it does seem plausible that if there's a bunch of zeros, maybe there's like an easy way to compress, but actually the way to compress, which I'm going to mention in a moment, is like, oh, what if we turn one of these threes into a zero? So you compress by deleting singular values, like you just turn them off in a sense. And that is like, because yeah, that does create more, but it has to be made more precise. But I was going to start more like with just some concrete examples that develop some intuition, and then I'll kind of like say a more precise sense of how can you use this to compress. But here's like a cute example, which is on the I may yeah, I'll try to play with my GitHub Copilot AI thing to tell me which Python code I should assign. But I mean, because it's a fun experiment where you can kind of like write some code to compress like an image. Take a picture of your pet if you have one and compress it. Like like so I'll do one like that. So but let me just show you like I put them at the end if okay. Yeah, so cute. Okay, so yeah, you can read. I'll kind of like tell you like the basics of what is happening in this page if you want to read it more later on. Okay, here's what's going on. Like, imagine that like this is kind of more like a statistician's perspective, right? You're measuring some data from some population. Maybe here, like I think he put like, or the person put like 20 data points, right? So maybe you're measuring the weight and the height of a population. It can be just two features, whatever you want, two features of some population, right? So there are two ways to, like, so each feature, like, has like two values, right? Like there are points on the plane, right? So you get like an X value and a Y value, an X value and a Y value, and an X value and a Y value, right? Because you made 20 measurements, you have like 20 of each, right? So this is naturally like, I mean, at least the way I set it up, uh, this is naturally, like, what a 20 times 2 matrix, right? So in the singular value decomposition, what you will look like, what you look at are like, you kind of like look at both possibilities, right? Like A transpose or A transpose A, right? Let's just like look at the sizes. So this one would have been like again, 20 times 2, and then the other one is 2 times 20, right? So A transpose A, oh, this is like the 2 by 2 matrix, right? And the other one would have, well, I mean, this one to be the 20 by 20, right? Like, because it's like a 2 times 20, and then 20 times 3, right? Okay, so of the two possibilities, like the two combinations, one is like gigantic matrix, right? That's like 20, it's like a 20 by 20 matrix, and the other one is like a smaller matrix, a 2 by 2 matrix, right? So for the cool thing again, what the singular value says is that both have the same eigenvalues, which is insane. Like when you think about it, right? It's like that's like amazing fact. So, but of course, of the two, right? If I had to interpret the data, which one would I prefer to use of the two? I would prefer to use like the 2 by 2 matrix, like the balance is pretty clear, right? And so what you could do is kind of find the eigenvectors of, of that 2 by 2 matrix, which anyways are used in the singular value decomposition, right? And then you kind of plot them, right? Here's explain. Okay, so this is kind of like, like the eigenvectors, you can make them of norm one, but so what they're plotting here is like the eigenvector times the singular value, so that the stretching factor shows a little bit more clear. And so what you see in the data is that the longer eigenvector is actually related to the direction in which there's more spread in the data, right? Because they're like kind of like the data spreads more in this direction than in the other direction of the blue vector. So kind of like the eigenvector with the larger singular value is the one where there's, but maybe not to be super precise with the terminology of statistics, but more variant, right? Like there's more like change in the values of the data points in the direction of the largest singular value. And so, for example, one thing you could do, right, which is kind of what they're describing in the in this discussion, which you can read. It's kind of like interesting, but well, but that is more like of yeah, but like this is like definitely it can be in any dimension, right? So like like that can be more confusing. But yeah, like but yeah, like I agree that's kind of like more like a gradient or something like that. But yeah, no, it definitely independent of that. But like for example, since this is the largest singular eigenvalue, you can kind of like think about kind of like doing like a projection, like you kind of can project the data points on the line determined by that eigenvector, which is kind of what they're explaining here. Like let's just say if you were to throw off, like just imagine ignoring the second component, like the second singular eigenvalue. Notice that this is like a tensor decomposition, right? So they're saying here's like a way to compress it to the question of how do you compress. Let's say you forget about the second component. Why? Because this is a smaller value of the singular value, and then that's how the data points now look. They cluster along that particular line. So it's kind of like a projection, you think. And then you could imagine, okay, well, I'll talk about the card in a moment. But then you can imagine kind of like, oh, okay, maybe like maybe you can play with the data where maybe it would have ended up being like 3 by 3, right? Like maybe one of these matrices ends up being 3 by 3. And then if you keep the largest two singular eigenvalues, then you project onto a plane, for example, if you wanted to do something similar. So kind of like the idea, or even, and this is kind of like the great thing, because like, even if the matrix had been 5 times 5, right? Well, if one of those two matrices had been 5 times 5, let's say the smaller one, I mean, again, you would find the singular, the singular values. You keep, for example, the largest 3 of them, and that's kind of like a box, a 3-dimensional box in, like they span a 3-dimensional space inside the 5-dimensional space, and then you can do a projection onto that 5-dimensional space, and then you bring it, you kind of like rotate it and bring it back to a 3D picture, so like you can always, like that's kind of like you can drop the dimensionality of the data that way by doing like a projection onto the space of singular values, yeah.
So I see that you essentially take like, you essentially decompose your data into like, linear combinations with eigenvalues.
Different singular values, yes.
Right, and that like scaled by some singular value.
Right.
Whatever that.
Yes,
And then you drop them off.
right.
Why do you, like, why is this more optimal impression than like dropping off some of their data?
Oh,
Like, why is this like nice thing to do?
oh, no, like I still haven't written it, but the idea is that, I'll write it in a moment, but imagine this like a matrix that had like a gigantic rank, like rank 100,000, right? Then you could ask, well, let me find a matrix of rank 100 that's closest to this matrix I started with. That kind of like the theorem, which is like the Eckhart-John theorem, which I'll write, is that of all the matrices of rank 100, the one that's closest to the original one is that one that you get by keeping the first 100 singular values. So it's kind of like the closest, like the one that you get by throwing off the remaining ones does produce kind of like the closest matrix in a precise sense of this. Like you just have to define a distance between matrices, which I'm about to do. Once you have a distance between matrices, you can ask which is like the closest matrix to another of a given rank, and that is the one that you get from just keeping the largest. So if you want to have a rank 50 matrix that is closest to a gigantic matrix rank, you keep the 50 largest singular values, and you throw everything else in that tensor probability
Yes.
function.
I'm sorry, I don't know if you guys like went over singular value last lecture.
Uh-huh.
But like, so what really are singular values? Like I'm not sure if I totally understand. Like,
Well, the idea
how
is,
do you sort of compute? Like,
Oh,
is it like
I
a
mean-
Taylor expansion?
No,
that
no,
you're
no.
Dropping off to this.
this is a symmetric matrix, right?
Uh-huh.
This has eigenvalues, right?
Right.
You call like an eigenvalue of this lambda, right?
Yeah.
The singular value associated to this eigenvalue is just the square root of lambda. They're just square roots of. They're just
It's
like-
the square root of the eigenvalue.
Yeah. That is done with the square root because again, if you think about it, in the case where the matrix is symmetric to begin with, then you want it to be kind of like plus or minus the eigenvalues if the matrix that you started with was symmetric. So
Wait, could you repeat that? How would it still be?
because if the matrix like the things like A may not be squared, so you cannot even talk about the eigenvalues of A. A may not have the eigenvalues, right? But if A happens to have eigenvalues, and for example, if A were symmetric, then this definition is just, in that case, would just coincide with plus or minus the eigenvalues. So it kind of like that way collapses to the regular eigenvalues of the matrix in the cases where you can compute the eigenvalues of the matrix. If that makes sense. Is that okay? So let me see. It's like kind of no, but I'll do it for my cat. What I was saying is like I will just play around with the code, like try it on my own. Like if I succeed, I'll kind of like.
Oh, it's just.
It's like in a website that I found, like, and then like but I posted the link on the Canvas site if you want to. Yeah. Oh yeah, this is cute. Well, okay, right. So this is kind of like the another fun application of this is kind of like, kind of like an image, right? So like, you imagine it being made out of pixels, right? Like here, I guess like, just kind of like closer to matrix notation. Just imagine that the I goes down and the J moves to the right. Okay. And so you have like, I think this is kind of, I don't know, like a 360 by times 360 matrix, right? And what is the value of each matrix? You know, if you're working on grayscale, you have maybe like a majority rule where like, you know, imagine like the grayscale going from 0 to 1 or 0 to 255, whatever, however you want to kind of like rule like the interval. And so if you know, you kind of like assign it a value between that. And then, you know, you can apply like a singular value decomposition. Okay, this is like a okay, so this is, yeah, this is what they're saying because it's 360. Okay, because the matrix was 360 times 360, there could be at most, right? There might be even up to 360 singular values, right? Some of them would be repeated for sure, but you know, if you include repetitions, like you know, you could find those. And so, what if you just keep the, you know, what if you do the decomposition of the matrix and you just keep the largest singular value? Okay, and this is what you get, like, you know, if you just keep the largest one, just one value, it doesn't obviously tell you that it is a cat, but at least it does tell you a little bit of the shading, you know, like where the intensity in the image was like, which is kind of what like the person is saying, that the brightness kind of like appears in the right places. Yeah.
So I heard you could like use this word that be pick like, let's say like, take a very high detail photo of a face, pick like 10. And you can kind of use that super simplified blur as a like recognition of someone's face. Hair, another.
I mean, I think, yeah, I don't know if they use that SVD per se because there are so many algorithms, so they may do like a more efficient algorithm, right?
Yeah.
But yeah, they all have kind of like a similar spirit, you know, like, yeah.
And that would be how they kind of, because you can't just take a photo and like, hair, there's that photo, it's a photo of the person, instead, take a photo and you reduce so much dimensionality, and then it's like, okay, it's this basically the same.
I mean, yeah, you have to, I mean, like it would be too much data, like in general, like just to do like a direct comparison. So yeah, you do have to compress something.
Yeah.
What I was going to say, oh, but this is cute. So you remember like at n equals 1, it was almost like a full blur, and now the images are showing you like what if you keep the first 5 largest singular values, like the 10 largest singular values, the 15 largest singular values. And you see already by n equals 20, and remember this could have gone up to 360, right? You know, maybe could have been 0 or whatever, but already once you get to n equals 20, that's like pretty decent enough. Also, yeah. Even here, I would say that you can kind of like show really nicely, you know, what the image is. And so there's well, and then the last thing that this website is discussing is that in the case of color images, you kind of like apply it to like RBG, like you know, you kind of like break it into 3 matrices and apply like SVD to each of those. Like you know, you do it for like a combination of the colors, which is what they're discussing here. But yeah. So. But oh, and this is kind of like this is a cool graph. You see like how the singular values decay quickly. In general, so like you know, kind of like do it, you know, like in a for a good compression, what will happen is that maybe the leading ones, the first ones are really high, and then everything falls down to 0 quickly, and then like that also gives you kind of like a sense. Oh, you can kind of like throw them away.
Is there like another like increase that
Well, okay, so here, this is in log scale, right? So it's not that, I mean, they're still always going down, right? It's just like the rate of, you know, yeah, you have to be careful because you're reading in log scale, right? But,
so
Mhm.
when you say throw away singular rounding,
Mhm.
do you mean that like twist them to 0, or do you mean that you want to throw away everything that corresponds to that?
So what I mean by that is that with the matrix, let's say, if you write the matrix in terms of the singular value decomposition, right? Let's say the rank of the matrix has been 100,000, right? By throw away, I literally mean that I truncate this sum up to 100, for example. Yeah, so like the approximation, which is kind of like what you know, it's kind of like similar to what you will do with the Taylor expansion, right? In a Taylor expansion, you give the leading terms. It's just that here, like the leading term are the terms with largest singular values. That's how you should think about this. So it's kind of, but it is, but so literally you throw everything, which is the same as what you get by formally setting to zero, the sigma i's up higher than 100, right? 101, 102. Yeah.
So essentially, if we have any matrix A, we know that it can be written as like, if it has a rank n sums of tensor products, then the singular value is the coefficient
Well,
of those.
you have to be careful because, like, if the rank is n, right? Then, right, if the rank were 100, it is a sum of 100 tensor products, right? But the singular value decomposition is like a very special type of decomposition of like 100 tensor products, right? So, this matrix can have like if the matrix is 100,000, there will be plenty of 100,000 combinations of tensor products that will give you the same matrix. But the singular value decomposition was one of the reasons that makes it super useful is that these vectors are orthogonal to one another, which is like a more specific type. It's kind of like similar to like a basis versus like an orthonormal basis.
It's like each of them add them, like they add, because they're
Orthonormal, yeah.
orthonormal, they add different dimensions.
In a sense, they contribute, right? Like different, right? Correct. Yeah. So but it's kind of like similar to a basis, like if you have a basis, there are plenty of different bases, right? So like a vector having a vector space of dimension 3, there are different decompositions, but sometimes they're preferred ones if the basis are orthonormal or whatever. Yes.
If you thought of like the tensor product that you be as kind of like, I don't know, let's say like a feature, and then you thought of sigma as like kind of like a weight. If you think of it like, if you normalize sigma to like values between 1 to 100, you kind of see which features of your data set have like the highest returns.
Well, I think, okay, so this definitely is used to, I mean, I should find this example to make it say a little bit more, something more concrete as well, like with these Netflix preference problems, like, where then you have like, like I think I can mention something like this before, where you can ask people to give a rating to movies or different genres, like drama, comedy, or whatever. And then, yeah, like the SVD can be used, like, kind of like sort out those preferences or like relations between like the movies from different categories. But I think you have to be like, it is, I don't want to say something that will be too precise, because, but it is used, yes, it can definitely be used to kind of like find relations between the different, categories that you're using like as features, if you want to call it that. But like the devil's in the details, they say. So like, but I'll see if I can, because I have read about that recently, but like I'll see if I can find the example we can like maybe mention it next time, like so that's a good one to decide. But you can think about it in the meantime, But like yes, this is one of the reasons why SVD is useful because it has, it does have like all this extra information, like like about what like because like that shows like the bigger collections in the data. So yeah, so okay, so this as I was saying, like and the other one is kind of like the other animation that I had. It's kind of like the same idea. I just liked it because it also had like more images to play with. So it's kind of like you kind of control it more easily, right? So like for example, this is kind of like keeping all of the singular values, and then you kind of like start, you kind of like start throwing more and more out, and then you can kind of like see how the images change as you kind of like you see now starts getting like now, but it took a while to kind of like like the picture to kind of like start losing like significant amount of quality, and they kind of go a little bit about like the compression ratio, like some like numerical things that are useful to.
In the more complex images, the higher its RAM.
Well, I guess that's right, it's chicken or egg, right? Because also like, how would you define the more complex well, you also have to say, right, if you were to tell me what is a more complex image, you could kind of turn it around and be like, well, it means that the rank is higher, So, you kind of like how these
Like
things work.
if it was like a blank image, like just a white screen, then.
Right, because every pixel is kind of like,
Of the same.
yeah.
Zero.
I agree with that. Yeah. Right.
In a sense that since it's zero rank, it's just a sum of one enterprise.
Right.
You can't throw away anything.
Yeah.
That's the only thing.
No, I agree with that. I mean, I do agree that that's like the right intuition, but then there can be competing intuitions, and that's why you get different measures of complexity, right? Like, so you have like kind of like this idea in your head of what this is also, I mean, I don't know if we'll get to talk about entropy, but that's kind of like the idea of entropy, right? Like, there's kind of like an idea of like information that a message carries, which is supposed to kind of like satisfy certain natural properties, but then like you kind of like take it as a definition, like as a quantitative definition of like, of what the entropy is supposed to mean. But sorry, of what information is supposed to mean. But yeah, so this is like again, this one is very cute. But yeah, it's like so it's kind of like fun, but I just thought like this is a good example to kind of think of more sense like in practice of how these things are understood. What I was going to write, maybe just to kind of like finish for today, kind of like in what sense this is an ideal approximation. I think that's good.
And is there some sense of, so for instance, in like phase diagrams, there's certain um phase changes that happen at a particular point. So is there some kind of, threshold at which you significantly start seeing depletion?
Well, I think okay,
Like all of a sudden you go beyond this threshold, you just start seeing blur.
I think I don't know if you would call it like a phase diagram, but I do think like again, I don't know like a precise statement on the top of my head, but there are kind of like rules of thumb, like coming from the central limit theorem and all these like statistical like that maybe after like after the rank, if the rank is R, maybe after root of R or something like that, past the root of R, you kind of like many times like it sometimes involves like the square root or things like that. But yeah, no, there are many rules of thumb in all these areas, like which I'm sure like some can be maybe more precise than others, but I imagine that there are some. I don't know, like if they're just empirically that you notice that there's certain thresholds, because I'm sure there are thresholds where people realize, oh, after you should keep this amount of singular values, for example, because either experimentally you realize that after the number, like it doesn't make much of a difference. Like, a better example is with like the frequencies, like, like maybe a bit of an overthink, but you kind of like you can do the same, like a similar idea with like, Fourier analysis or things like that sort. And you could keep frequencies like with the human ear kind of here. Like just for obvious reasons. Obviously, like you could like even go beyond that because like I'm sure like you don't even need to go, that extreme, and then you can throw more out. Like, but I'm sure like there are neurological considerations you could bringing to bear that also would give you some insight as to what matters and what doesn't. But yeah, like maybe just to this is like a cute thing to mention. It's like a very easy proof, so I may kind of like I may put it like as an optional problem. I don't know. But yes, like just to kind of like talk about in what sense this is like a good approximation. Like so singular values and approximating matrices. There is a way to measure distance between matrices, which is useful to go over. And I'll just start kind of like with how do you measure distance between vectors, because once you have that, you kind of like realize what the formula should be in this case. So how do you measure distances between vectors? Like Oh, so here's like a way to do it. I'll even draw the vectors, right? Like if you had like a vector u and a vector v, right? Kind of like the distance between them, right? Is kind of like the length of this vector, which you can think of as being u minus v, right? Or v minus u. So the distance between two vectors, like I'll write it as the distance between two vectors u and v is just the length or the magnitude, right? Like the norm. That's another name for it. The norm of the vector u minus v. Reasonable. Okay, and then you ask, okay, how do you find that? Okay, now I'm bringing the question like a step further. Then you could ask, okay, how do you find the norm or the magnitude of a vector, right? So then how do you find? Which kind of like seems silly because you like you can apply Pythagoras theorem or whatever. But actually, what a more clever way to think about it. Well, I'll still kind of like write it down in that answer in that format. You could say, well, the norm is just like, or the magnitude is just u1 squared plus u2 squared plus u3 squared up to un squared, right? But isn't that the same as the dot product of u with itself? So actually, that's kind of like a more clever definition. Like that is like a convenient way to find the distance between two vectors. You basically realize, let me put like the two important things here. So the two important formulas for now is that the distance, that the distance can be computed in terms of like the magnitude or like the norm, which is like the magnitude computing to this. And the norm or the magnitude can be computed in terms of a dot product. So the idea is that the moment you have a dot product, so the idea is that the moment you have a dot product, you get for free a magnitude, a notion of magnitude, and you get for free a notion of distance, if that makes sense. So the moment you get a formula for the length or the magnitude, and then one for the distance. That okay? Does that make sense? So my question of how to measure distance between matrices just boils down to how do you measure a dot product? What is a dot product between matrices? Like that's all that you have to define. So what is a dot product between two matrices? Well, that's usually called like an inner product, but for now, I'll just call it like a dot product between matrices. And I mean, for what it's worth, you can kind of like go by analogy, try to see like the diagram helps you out to some extent because if you had two vectors, right? In fact, we may have discussed this already, but if you had two vectors u and v, right? You can think of their dot product as just being like what you get when you stick them together, like And if you think of two matrices, like take two matrices of the same size. Okay, so let's say you have a matrix A. And they don't have to be square matrices, by the way, but they do have to have the same size. So I'll kind of like specify that you have two matrices A and B, which are n by n matrices. Okay. So matrices have two legs, right? They have two indices. And then you just contract them both, and that is a dot product. It actually, you can check that if you all dot product has to satisfy certain requirements, but you kind of like check that it does satisfy the desired requirements. So like the fancy notation of writing a dot product, which I think I may have mentioned before, is just like and we should figure that into this notation. But it just like instead of putting a dot, just put like the two things in question, and you put like kind of like brackets around them. So from this definition, it's kind of like just if you it just ends up being two sums because there are two contractions, and then like some multiplications involved. So you just do. Let's say that I guess I goes to from 1 to m, and j goes from 1 to n. And then you do like that multiplication, so that you get like two and a I j e I j. That happens to be, there's like a more fancy way of writing this dot product, which is in terms of a trace. Like if you kind of like just, it looks more elegant. But it's kind of like the same. It just ends up being the trace of this matrix. That does like that does need some, you have to kind of like write it down like so that you convince yourself that you get the same answer, but it does really matter. It's just like a more elegant way of writing. It makes more clear for the public, it's more transparent. Yeah.
So in general, like I didn't see why this would be overlooked. It's either product which they define for unit answer.
Oh, right, no. Yeah, you could right, like that's like yes, like yeah. Like you can also give like you just join their indices. Yeah. Like it's a massive contraction. Yeah. And this is sometimes called like the Frobenius inner product, if I'm not mistaken. And so, for example, if you believe in this definition, and this is kind of like the fun part. If you believe in this definition, what would be the magnitude of a matrix? Maybe just to kind of like, I'm almost done. But what would be the magnitude of a matrix, right? I'll put F for Frobenius so that we know that it's related to that. It is the square root of the dot product of the matrix with itself, right? The dot product of the matrix with itself. No, this is a number, right?
Oh, yeah.
Yeah. The scale and dot product. Sorry, I should have given a definition of a dot product. Right? Dot product is kind of like in general, it's a number, symmetric, right? Like it doesn't matter in which order you take them. It has like the usual properties of dot product that you remember between vectors. They more or less are demanded for matrices or functions. There's a dot product between functions. I think I mentioned that before. So yeah. It's so, but if you go back to fancy notation, like in terms of the trace, Oh, but isn't this like the matrix that appeared in the SVD, one of our friends from the SVD? And so what is the trace of a matrix? In general, the trace of a matrix is the sum of eigenvalues of the matrix. We can kind of like show that. So this is the sum of the eigenvalues. I mean, I don't know how many eigenvalues. I mean, we'll see that doesn't matter too much. But let's put it like this, like where lambda k is an eigenvalue of a transpose, but you know that the only ones that are non-zero, right? How many non-zero eigenvalues does this metric has up to the rank of A, right? It's the sum of the squares of the singular values, right? So isn't that like a Pythagoras theorem almost? Like you're squaring, like uh I mean, it's kind of like a Pythagoras theorem, right? Like it's a sum of squares, right? Like it's just like the replacement of the sides of the triangle are the length of the singular values, right? So so that's the Frobenius, and then like once you have that formula, like the distance between two matrices, the distance between two matrices is just like what I was telling you. The distance between two matrices is the length, or like sorry, the Frobenius the magnitude of A minus B. The Frobenius magnitude. You can, right, with the dot product, you can, but with the inner product, yeah. I mean, right, like, so, yes, and then you can say whether they're orthogonal or not, if their inner product is zero and.
So I was wondering from the video and also this class, why the whole time, it just felt slightly arbitrary why we took the square root of the lambda, but is it because they initially started here and then they
Well-
built it backwards, because this is kind of like,
I mean,
they did it.
I mean, I guess that could be. I mean, I don't know how it happened. Like, I could believe that that's how it happened. I also could believe that it was just like the thing that if the matrix happened to be symmetric and square, then you want the singular values to just. Yeah, I think for me those are like the two more obvious explanations for how But this is like it's not, at least not for me. Like the history is always messy, and many people think it at different times, and maybe some people thought about it and they didn't even think about giving it like a name because it was no. But yeah, like this is definitely a reason why you might want to define them that way.
Is it a coincidence that it resembles so much to, like, the Pythagorean theorem?
Well, I mean, it's not a coincidence because in a sense, in the singular value decomposition, these are orthonormal. The eigenvectors are orthonormal. And so it's kind of like inheriting, they are kind of like like orthonormal axes, like the VI's and the sigma i's. So you would expect that the length square of the matrix is kind of like, you know what I mean? Like, if you have
Orthogonal is like the.
perpendicular, sorry, yeah, these are kind of like perpendicular directions. So they are kind of like the analog of IJ and K, and so you would expect that the length square to be this,
Are they like, which like, the magnitude is one?
yeah, the length is one, right? Like that's what the
So
norm.
kind of stretches.
Right. But that's what orthonormal means. Like they're perpendicular and they have length one, right?
Technically, the length is.
Yeah,
So you just.
right.
So it's kind of like.
There's a sense in which, like in the space of matrices, this is kind of like an axis, and this another value gives you another perpendicular axis, like and yeah. So that is why you would expect it to be true. What I was going to say, like maybe to wrap this up, in case there are some questions, is that this I mean, I don't know if there's like an H here. I should in the name, but the Eckhart job, I think it may have an H. I'll kind of like this is where you wish. Oh no, it has no H. I'm glad I wrote it. It's kind of like almost like I'll just make a picture. I'll kind of like be abusive of the if you thought about kind of like a space of matrices of rank less or equal to some number, right? Let's call this number P or whatever. You have a space of matrices whose rank, where all the matrices whose rank is less than P live here, okay? And then you have a matrix A, which I'll kind of like almost draw as a vector, right? Just to kind of like make the analogy that you should really think that you're kind of like applying a lot of like vector analogies here. And so you're asking for which is the matrix that's closest to the matrix A that minimizes the distance, right? There should like, I mean, at least from the picture, of course. You could try to find like the matrix A that is a matrix closest in the sense of distance, like now that we have a distance function, the matrix closest to A whose rank is less or equal to P, right? And what Eckhart John says is that you do the SVD and then you just keep the first P terms, like that this matrix is just like the truncation. If you think if you think about this in terms of like the singular value decomposition, where this goes from 1 to the rank. So Eckhart John says that this is just like the first. The proof is super easy actually. So I'm gonna put it like this. I will give some hints if in case someone wants to prove it by themselves. But it is like a very clever proof, but it's not that hard once since we already have proven a lot of stuff about the singular value decomposition. So again, here like with the understanding that the singular values are arranged in decreasing order. And then like maybe so this could also be fun to do. You can also apply this idea to do like a singular value decomposition to a derivative or like an integral operator, like like so that involves something that's called like a cosine transform and so like like the ideas can be explained in any ways, but it's not like and I thought like I should mention this today and then to see kind of like that is like a very useful result. And there's also other applications to pseudo inverses, which is also maybe worth bringing it up because that's also like a useful idea as well. No, the singular value decomposition is really a climactic point of linear algebra, right? Like because it applies to rectangular matrices, which is insane. Like most of linear algebra, just if you think about it, it works really well with square. And with rectangular, you have to be a bit more clever. And this is like a very elegant character, like way to understand like rectangular matrices as well.
These singular values, they're basically eigenvalues for the rectangle.
It is what you read. If someone twisted your arm and forced you to give an answer for what's like an eigenvalue of a rectangular matrix, you say, oh, it's a singular value, right? Because in the case that the matrix is square and the matrix is symmetric, they are literally just the eigenvalues up to a sign. Like they're in absolute value because they're positive, right? Like the eigenvalues can be negative. So they're kind of like the absolute values of the eigenvalues, like the eigenvalues in absolute value, like but I mean you can ignore like the absolute value part. Like yes, like up to a sign, that's how you would define the eigenvalues of a rectangular matrix. That's kind of what makes sense.
Why did they not have the sign included as well?
Oh no, it's just the thing is like the matrix, the matrix, the matrix A transpose A, this one or this one, they're naturally non-negative in the sense that their eigenvalues come out positive.
Oh.
So I mean, not from these ones, right? Like yeah, like I guess like you could like not like directly from these ones because they make always like the eigenvalues non-negative. You see, like so the sign, like I agree that that's not something like maybe you can retrieve. I mean directly from this construction, but let's just
So for the you just keep these singular values by you just take the largest.
Essentially, it kind of boils to that and the fact that this norm this distance function is what people call is rotationally invariant. So if you rotate all the factors, the distance is the same. But the idea, again, I'll write the hints because it's actually like a super quick proof. But the idea is like if you remember, this is kind of like the matrix format of the SVD. And if you know that the distance is the same, if you rotate the matrices by rotation matrix, then it's kind of like you reduce it to the case where the matrix is diagonal. And if the matrix is diagonal, it's like straightforward, you know, like because then the singular values are just like or like almost diagonal, like um I mean, like you can reduce it to the case where you're proving this for sigma, the matrix sigma, and there is kind of like obvious like formula. And so, but yeah, it uses and there are other ways to measure norms between matrices. I mean, there's like again a lot of theory about matrix norms. This is called matrix analysis or matrix calculus. You're right, like you just do calculus on matrices. So there are other ways to do this, but and the theorem, the cool thing is that it continues to be true as long as the norm that you use is rotationally invariant. So it's more general than this. But okay, let's end here. I do have to leave earlier today because I have to be in New York in a bit. But I can answer a couple of questions for a couple of minutes, and if not, we can just talk more. I will give you extra office hours on Tuesday if you look at the announcement. But yeah.
There's the SVD generalized higher order super.
Well, the tensor train, which we'll talk about, is kind of like a replacement for the SVD. But the proof uses SVD. But it's kind of like that SVD version of a for a tensor, but it's not as amazing because again, the matrices have too many coincidences. But it's kind of like, again, if you were forced to do an SVD for a tensor, kind of like the thing that you come up with is like the tensor train, which I'll talk about. Yeah. So there is like a version of that. Yeah. Well, yes, in the sense that again, like I think this is like a fun example. I may do it. If you kind of like if you have like the derivative, I mean I'll maybe not next time. I don't know if I'll do it next time, but you know, like the derivative is also like kind of like a linear transformation, right? It's just like here you do have to be more precise by what you mean by functions and functions, right? Like which functions do you want to apply the derivatives to? But then if you just kind of play with the analogy here, if you want to do, you can try to do like an SVD to singular decomposition to a derivative, but for that you would need like kind of like the transpose of the derivative, right? Which you can define. So you can define like the transpose of a derivative or the yeah, it's called the adjoint actually. Like so, and then once you have that, then you can kind of I mean, I can kind of like spell out some of the details. It ends up being minus d squared. So it's minus the Laplacian. That's how it's called. Like, and then if you solve like an ODE on the like you know you can kind of like solve this equation. If you try to solve this equation, which is an eigenvalue problem. I don't know if you saw that as an ODE class. You will find that the eigenvalues are not negative. So it's kind of like the same idea. And it's in terms of sines and cosines, if you restrict it to spaces of periodic functions. So it is really more or less the same story. It's just like with series instead of finite sums. And more or less everything goes through if you choose the right functions to act upon. And
You should actually find like the rate, this like the rate, sorry, that you can apply to any function.
well, I mean, the thing is like the derivative, again, like you could try to do kind of like multilinear maps involving the derivatives, but there's a little bit like, you know, you have to be, you know, you have to make sure how you want to generalize the ideas, right? Although I was saying is like, in a sense, like a derivative is kind of like an infinite dimensional matrix. That's kind of like the analogy to have in mind. So I'm applying SVD to infinite dimensional matrices. That's what.
No, I was thinking like, oh, you can do that for derivatives.
No, right. And then the integral is like a pseudo inverse of the derivative, which is also fun to see. Like, yeah. Right. Yeah. It's kind of like an inverse, almost.
So I started seeing everything that's like.
Right. That's like yeah. Correct. Right. That is in a Hilbert space. That's how it's called. Like, yes. Sorry. Were you going to tell me?
Let's be singular value decomposition. Essentially, to apply that we have a trunk theorem. But for certain functions, that function doesn't have some values.
Right. The case of the derivative is a little bit more tricky because the eigenvalues do explode to infinity. but the eigenvalues of the integral, because it's the inverse of the derivative, shrink to zero. So those like do kind of like decay to zero, but the derivative is a bit more tricky. Yeah. Sorry, were you going to ask me something?
We have to look at the
Oh yeah, just upload it at some point. Like, did I make it on Saturday or?
Yeah.
Oh yeah, just do it on Sunday whenever. Like, yeah, don't worry about that. Just do it. You know, and if in fact, if you want to wait until Tuesday so that you can ask me about it during office hours on Tuesday, you can also do that. Like, there's no rush with the assignments. It's just for you to kind of like keep your minds busy. But yes, let's finish here and then I can still answer some more questions.